So today's speaker is Jonathan Ouellette, who got his PhD from Berkeley and is now a postdoc at MIT. He's been working on a couple of experiments searching for dark matter, axion dark matter, and also measuring neutrino properties with neutrinoless double beta decay searches. And he'll tell us about his work. John.
So my talk today is called Searches for New Physics at the Edge of Absolute Zero. And I'm going to be telling you about two projects that I work on. And what they have in common is that they're both very, very cold, hence the name Edge of Absolute Zero. Really, they address two very different questions that I believe are on the forefront of particle physics research. And so the first one is, why is there something in the universe rather than nothing? And to get at this, I'll tell you about the search for neutrinoless double beta decay and the experiment that I work on called Core. And the second is, what is the origin and nature of the dark matter that comprises some 86% of the matter density of the universe? And to get at this, I will tell you about the search for axion dark matter and a new project that we've been putting together at MIT called Abracadabra. Let's begin with the fairly broad question of why is there something in the universe instead of nothing? So now you might be tempted to say, well, everything was created in the Big Bang, and that is why there's something instead of nothing, and this is broadly true as far as we can tell. However, what should have happened immediately after the Big Bang is we should have produced a whole bunch of matter and antimatter in roughly equal abundance. And then as the universe cooled, the matter and antimatter would pair off and annihilate. We would wind up with a bunch of high-energy gamma rays, which as the universe cooled further, would redshift down to low-energy photons. And you'd wind up with a universe that was filled with nothing but those photons, so you'd look out into the night sky and you would see nothing. It would be very boring. In fact, we wouldn't even be here to be bored by how boring it was. But this is clearly not what happened. We look up into the night sky and we see a whole bunch of stuff. And as near as we can tell, all of that stuff is made out of matter. And that's significant because it could have just as easily been made out of antimatter. So what we believe happened was that at some point in the early universe, there was some process that converted a little bit of that antimatter into matter. So that when that great annihilation happened, there was a little small remainder of matter left over that went on to form everything that we see in the universe today. So now you might wonder how big this asymmetry has to be, and it turns out that it doesn't need to be very big at all. In the early universe, you need something like 10 billion and 1 particles of matter for every 10 billion particles of antimatter. And then this 10 billion will annihilate with this 10 billion, and this 1 in 20 billion particles goes on to form everything that we see in the universe today. All the structure that we see in the universe came out of this 1 in 20 billion particles. What is this process that converted antimatter into matter? It turns out that we don't know what that process was, but there are a couple of things that we can say about any process that could do this. And these conditions are known as the Sakharov conditions. So the first condition is that you need a process that violates baryon or lepton number. And this is just a simple statement that if you want to convert antimatter into matter on cosmological scales, you need a particle physics process that can convert antimatter into matter. And so that's fairly obvious. The second statement is that you need CP violation. And this is just the realization that if you can convert antimatter into matter, you can also convert it back from matter into antimatter. And if they happen at the same rate in both directions, you wind up with a wash and no net asymmetry at all. So you need this process to happen faster, going in one direction, and slower in the other direction, and this is just exactly a statement of CP violation, or a fancy way of saying that is CP violation. Finally, in the early universe, you need a departure from thermal equilibrium, and this is just so that the occupation numbers in the early universe can change, and this is relatively easy to satisfy in a universe that is rapidly expanding and cooling. But the one of these that I'm going to be talking about today is a particular process that violates lepton number called neutrinoless double beta decay. So to understand neutrinoless double beta decay, it is useful to start with the question of how are neutrinos different from antineutrinos. So usually when we talk about particles and their antiparticles, you say that the particles are exactly the same, but they just have opposite charge. And so, for example, you have the electron and the positron. These particles have the exact same mass, they have the exact same quantum numbers, but one has a charge of -1 and one has a charge of +1. You cannot say a similar thing with the neutrinos because the neutrinos do not carry charge. So you can't distinguish neutrino from an antineutrino just from their charge. If you want to get a little bit more technical, you can say something like neutrinos are all left-handed and antineutrinos are all right-handed. And this is a statement about the chirality of the particle, which way the spin is relative to its direction of motion. And this is a true statement, as far as we can tell. But there are, electrons can be either right-handed or left-handed. We don't say that right-handed electrons are the antiparticle of left-handed electrons. So this is not a good way to distinguish them either. It turns out that the difference between antineutrinos and neutrinos are that antineutrinos are produced in processes that produce leptons, like electrons and mu minus and tau minus. And neutrinos are produced in conjunction with antileptons, like positrons or mu plus or tau plus. And thus we assign to the neutrino a lepton number of +1, and the antineutrino a lepton number of -1, and say that the universe conserves this thing called lepton number in all processes. And so this is a constraint that we have put onto the universe, but it is rather artificial. We have just created this constraint and said that the universe obeys this, but the universe may not necessarily disagree. So let's say that this is wrong. What if, in fact, neutrinos and antineutrinos are actually just different chiral states of the same particle? What if one is just the right-handed state and one is just the left-handed state of the same particle? If this were the case, there would be what is called a Majorana neutrino. And a Majorana neutrino would have really interesting implications for our understanding of the universe. To begin with, a Majorana neutrino is actually a low-energy relic, is inserted into the standard model as a low-energy relic of some high-energy physics. And so it turns out that this can immediately explain why the neutrinos are so much lighter than all of the other particles that we know about. And this is through this so-called seesaw mechanism, that the neutrinos become very light because there is some other mass scale that is very, very heavy. In fact, in order to produce the rough scale of rough mass scale of the neutrinos that we see today, this heavy mass scale needs to be around the grand unification scale. So this is maybe suggestive of new physics at the gut scale. But more to our current point, if the neutrino and antineutrino are actually just different chiral states of the same particle, then they can't have opposite lepton number. And in fact, the neutrino provides a mechanism for converting antileptons into leptons. And so it may very well be that the neutrino holds the answer to why there is something in the universe instead of nothing. And so this is a very interesting question to ask. In order to search for this, we search for a process called neutrinoless double beta decay. So in order to understand neutrinoless double beta decay, I'll first tell you about 2-neutrino double beta decay. And 2-neutrino double beta decay is a second-order weak decay in which a nucleus spontaneously converts 2 neutrons into 2 protons and produces 2 electrons and 2 electron antineutrinos in the decay. This is really just the second-order version of your everyday beta decay. This is a second, but it is, yeah, so this is a second-order decay. This process is allowed within the standard model for any nucleus for which it is not kinematically forbidden, for which it wouldn't require energy in order to conserve, but it's only been observed in about 10 isotopes. And the reason is that this is the slowest process that has ever been observed. The typical half-lives for this decay are in the range of 10 to the 19 to 10 to the 24 years. And for reference, of course, the age of the universe is only 10 to the 10 years. So this is a very, very slow decay. Typically, we only can see this decay in isotopes that have this very peculiar property, that the isotope is unstable to beta decay. It wants to decay down to this more tightly bound state, but it can't proceed through a cascade of 2 beta decays because the first step in that chain is kinematically forbidden. It would actually require energy in order to undergo a single beta decay. So the only decay channel available to it is that double beta decay channel that we're interested in. Neutrinoless double beta decay is the exact same decay, except without the production of any antineutrinos in the final state. This process would violate lepton number by 2, and you can see this because there are 2 leptons, there's 2 electrons in the final state, without any antineutrinos to balance them out. And this decay can only occur if in fact neutrinos are indeed Majorana fermions, or if, in other words, if they are their own antiparticle. So conceptually, you can think about what's happening as this is the same as the last decay, where 2 neutrinos are produced, but since they are their own antiparticle, they annihilate inside the nucleus without ever making it out. So conceptually, you can think about that's what's happening. This process has not yet been observed. The current lower limits on the half-life are in the range of 10 to the 25 to 10 to the 26 years. So there's a lot of ways that we can model the physics of what is happening. I'll go through this fairly quickly. The only thing that I need to get to is this plot here. We can typically decompose the half-life into 3 terms. There's a kinematic term, which just has to do with the density of states of the particles emitted in the decay. There is a nuclear physics term, and then there is this term that we call the effective Majorana mass. And what is important about this is that this is the parameter that we use to compare all isotopes, all searches for neutrinos double beta decay. This is basically our figure of merit that we're searching for. And it is a property of the neutrino mass. So there are 2 allowed parameter spaces for this effective Majorana mass. There is one for this so-called inverted hierarchy region, and one for this so-called normal hierarchy region. And neutrinoless double beta decay experiments measure down from the top, and direct neutrino mass experiments measure in from the right. So this is a plot that you will see later in this talk. So that is the main takeaway of this slide. The experimental signature, on the other hand, is relatively easy to understand, and this is because we do not measure the, in our detectors, we do not measure the neutrinos. They escape our detector. Instead, we measure the kinetic energy of all of the other particles emitted in the decay. So 2 neutrino double beta decay creates this broadened energy spectrum, which stretches from 0 keV, when the neutrinos carry all of the kinetic energy out of your detector, all the way up to the Q value of the decay, where the neutrinos are produced at rest, or effectively at rest. Neutrino-less double beta decay, on the other hand, has no neutrinos, and thus detects the full energy of the decay. So what we're searching for is this narrow peak at the end point of the 2 neutrino double beta decay spectrum. It is worth pointing out, again, that this is the slowest process that has ever been observed, and this process here is some at least 5 to 6 orders of magnitude slower. So this is really a very tiny signal that we are looking for. And because this is such a rare decay, we can write down a set of requirements that any experiment searching for this decay should satisfy. So first of all, you want your detector to be very large, and this is just so that you can, if you're searching for something that happens very, very rarely, you want to give it as much a chance to occur as possible. You want to instrument as many nuclei as you can. The current generation of experiments are instrumenting something like hundreds of kilograms of active isotope, which corresponds to something like 10 to the 27 nuclei that you're observing at once. You want your detector to have a very low background. This is so that if you have any kind of naturally occurring radioactivity or anything that builds a signal on top of this, it will very quickly mask the signal that you're looking for. So you want your detector to be very clean and have no background events. You want your detector to have a very good energy resolution, and so that is so that you can easily distinguish this peak from this nearby spectrum over here. And finally, you want your detector to have a high detection efficiency and runtime, so that if the decay occurs, you will have a good chance of seeing it. So the experiment that I will be telling you about is the Cryogenic Underground Observatory for Rare Events, or CORE. And CORE is a collaboration of about 150 researchers from about a dozen institutions, primarily in the United States and Italy. CORE is located at the Gran Sasso National Lab in Italy. This is a picture that was taken nearby. One of the perks of working on CORE is that you do get to make frequent trips to Italy, and I can say that I have immensely enjoyed the food and the wine, and the views are not so bad either. Unfortunately, the view from the lab itself is not so good, and that is because it is about a mile underground. And the reason that you go underground is because if you tried to do an experiment like this on the surface, you would just be inundated by cosmic rays. You would see nothing but cosmic rays all day. But by going underground, you have this 1,400 meters of rock overburden, which reduced this muon rate by about 6 orders of magnitude. So in Quarry, we are studying the isotope tellurium-130. Tellurium-130 has this nice property that it is unstable to beta decay. It wants to decay down to xenon-130, but it can't decay through this iodine-130 because it would require energy in order to decay up to that. Tellurium-130 also has a high Q value, which is good for kinematics. It means that there's about 2,500 keV of energy that is released in a decay, and that is a lot of energy, relatively speaking, and so this is good for detection. And finally, tellurium-130 has a high natural isotopic abundance, which means that it is easy to collect and easy to put into our detector. So in Quarry, we use a bolometric readout approach, which means that we convert the kinetic energy released in our decays into small changes in temperature of our detector. So a Quarry bolometer consists of an energy absorber, and the job of the absorber is to just absorb the kinetic energy and then warm up. In our case, the absorber is a tellurium dioxide crystal, and since it is made out of tellurium, it is actually also the source of the decays that we're interested in. So when a decay occurs, it occurs already inside our detector. This gives us a very high detection efficiency. To each one of our crystals, we attach a thermometer, which continuously measures out the temperature, as well as a weak thermal coupling to a heat bath, so that after the decay occurs, the heat flows out and the bolometer can reset. So when a decay occurs in one of our bolometers, we see a sudden rise in the temperature, followed by a slow decay back down to baseline, and the amplitude of the pulse tells us the energy that was deposited. To give you a rough idea of the numbers, a Quarry bolometer is about the size of a Rubik's Cube, but weighs about 1.5 pounds. That's about yay big. And we operate these detectors at a temperature of 10 millikelvin. So these are very, very cold detectors. And the advantage of this technique is that we can achieve a very good energy resolution. Remember, this was one of the requirements of our detector. We typically aim for about 5 keV full width half max at a signal of about 2.5 MeV. This is measuring our energy down to about 0.2% uncertainty on our energy. So this is on par with what you can get out of some of the best germanium semiconductor detectors, though not quite as good. So in Quarry, we take our bolometers, we arrange them into these 2x2 arrays. We stack the array 13 stories tall to form a tower of 52 bolometers. And the Quarry detector is an array of 19 such towers for a total of 988 bolometers, or 741 kilograms of tellurium dioxide, with 205 kilograms of that being our isotope of interest, tellurium-130. All of this is then mounted into the Quarry cryostat, and the Quarry cryostat is what cools us down to our operating temperature, and is actually a technical achievement unto itself. It is the largest, coldest dilution refrigerator in the world. It cools about 15 tons of material down to 4 Kelvin, with 1.5 tons of material sitting at 10 millikelvin. And it turns out that when it is running, it is actually the coldest cubic meter in the known universe, which is pretty cool. Yes, I make that joke. Okay, so Quarry originally got cold in early 2017, and we spent much of last year really commissioning the cryostat, getting our detector into a stable working configuration. But we were able to take about 6 weeks of data in the summer in 2 data sets. So what I really want to emphasize here is this is the data accumulation from the Quarry 0 experiment. This was the predecessor to Quarry. It ran from 2013 to 2015. This was my PhD thesis was on this experiment. And so it ran for 2 years and accumulated data at this rate. Quarry ran for 6 weeks and accumulated data at this rate. So between the increased data rate as well as the better sensitivity of Quarry, my PhD thesis was actually made obsolete within about the first 5 days of Quarry data taking. So that was exciting. So I don't have time to tell you all the details of our data analysis procedure, but I'll just cut to the end. We do perform a blinded analysis, but this is what our data looks like once it is unblinded. Our final fit will be to this gray region here, but this is sort of what is going on nearby. There is a flat background on which we are searching for a signal. And there are some nearby, this is a gamma line from just naturally occurring radioactivity located in our cryostat. This is a 2.6 MeV peak. So zooming into that region of interest, we perform a fit. Our model consists of 3 components. We fit that flat background, we fit a cobalt-60 line that is nearby, and then we posit a line for a potential signal at our neutrinoless double beta decay position. It turns out that our best fit is consistent with a negative decay rate, which of course is not physical. Our fit is consistent with about a 2 sigma downward fluctuation in the background, and this is a largish fluctuation, but 2 sigma happens from time to time. So because we didn't observe neutrinoless double beta decay, we set a lower limit on the half-life, and that, using just Cori data, corresponds to about 1.3 times 10 to the 25 years. And we can combine this result with the result from the Cori 0 experiment, which ran from 2013 to 2015, as well as the predecessor to that, which was called Cori Chino, which ran from 2003 to 2008. To form a combined limit, this is the limit on the neutrinoless double beta decay half-life of tellurium-130 from all volumetric tellurium-130 experiments of 1.5 times 10 to the 25 years. So this is actually the most sensitive search and strongest limit on this half-life to date. We can convert this into a limit on the effective Majorana mass. This is this M beta beta parameter. I told you this plot would be coming back. So the lower limit on the half-life corresponds to an upper limit on this effective Majorana mass parameter. And that limit is actually 140 to 400 millielectron volts. If you're wondering why there is a range of values, it is because to get to this, we have to divide by that nuclear physics term. And it turns out that that nuclear physics term comes from a theoretical calculation which has a factor of 2 to 3 uncertainty. So there's a factor of 2 to 3 uncertainty on our upper limit. So that upper limit corresponds to this yellow band up here. I'm not sure, I hope you can see that. There's this yellow band up here. And you can compare, this is our current limit to some other limits from other isotopes that are currently running or have been running recently. So this is where we are now. Where we would like to be in about 5 years is down to this blue band here. And of course, the farther down you go, the more difficult it is. So that's why we take about 5 years to get a factor of almost 10 going down. So this is, we will spend the next 5 years or so reaching just the top of this inverted hierarchy band. So that is the next 5 years. What about the 5 years after that? So the next generation experiment is something called Cupid. Let's see, so the field of neutrinoless double beta decay searches